Hi, my name is Bruna and I am a PhD student at LMMP, PUC-Rio. Today I'm going to present the work entitled Production of Microcapsules for Controlled Flow Behavior in Confined Channels, which was developed with Professor Mariano Michelon and Professor Márcio Carvalho. Microcapsules are formed by a core material involved by a shell. They range in size from 1 micron up to a few millimeters, and they can have a single core or multiple cores. Microcapsules are applied in several sectors of industry, when a physical barrier between the core material and the external environment is required. They have been used for encapsulation of cosmetic components as anti-aging elements, essential oils, and skin moisturizing agents. They allow the incorporation of sweeteners, colorants, vitamins, as well as of probiotics to different foods and beverages. Microcapsules can also carry the rejuvenator needed in self-healing methods of asphalt pavements. In pharmaceutical area, they are applied to reduce adverse reactions and side effects, allows site-specific and sustained drug delivery, increase shelf life, and act as an alternative administration mode of some medicines. Basically, microcapsules isolate their cargo and ultimately release it in a controlled way. In general, the release will be a consequence of mechanical rupture, biodegradation, dissolution or melting of the shell, or diffusion through it. Different triggers can be applied to activate the core release, such as temperature, pH, osmotic pressure, and external stress. Dynamics of deformable microcapsules in confined flows is relevant for medical, pharmaceutical, food and cosmetic industries, since constrictions are present in physiological systems, as arteries and veins, for example, and capsules are regarded as adequate models for living cells. Moreover, with a good characterization, constricted geometries can be used for triggering and controlling the release rate of a cargo by applying the necessary external stress to the microcapsule. Besides that, recent studies have shown that microcapsules may also be used in enhanced oil recovery as fluid mobility agents that lead to flow redistribution in the porous space, resulting in increased volumes of oil recovered. In addition, these same capsules can be filled with chemicals, such as surfactants, acting as carriers for target delivery in specific areas. As you can imagine, the adequate properties for each kind of application is different. Capsules used as vehicles for target delivery, for example, must be easily ruptured at certain conditions, while capsules used to improve mobility ratio or IOR cannot rupture. Controlling the encapsulation process and release characteristics of the microcapsules is essential for an appropriate application of these elements. This ultimately depends on the technique and material chosen to produce them. So the goals of this work are to design microcapsule suspensions with tunable mechanical properties, to study the flow of a single suspended microcapsule through a constricted capillary, to establish conditions at which microcapsules rupture or not, and to define pressure drop as a function of flow conditions and microcapsule properties. Let's start with microcapsules production. Our microcapsules are basically oil and water and oil double emulsions that go by a gelation process. In order to compose the microcapsules, sunflower oil is used as core and as continuous phase in which they are suspended in, while gellan, which is a biopolymer capable of forming hydrogels in the presence of cations, is used to form the polymeric shell. Because many applications for the gellan microcapsules require an oil-free capsule dispersion, we apply a recovery process to change the continuous phase from sunflower oil to acetate buffer after producing the capsules. There are many methods to produce microcapsules. The conventional techniques usually require two emulsification steps, present poor reproducibility and poor control of size and shell thickness. Therefore, we use this 3D microfluidic device that combines cold flow and flow focusing and allows the production of oil and water and oil templates with tunable mechanical properties. The device has two aligned round capillaries inside a square one, the injection on the left and the collection on the right. The inner phase flows inside the injection capillary, while the middle phase flows in the space between the collection capillary and the square capillary. The continuous phase, in turn, flows in the opposite direction between the space between the collection capillary and the square capillary. As I mentioned before, after producing the capsules, we disperse them in acetate buffer. So in the end, we have an oil in water system. Then, to produce perfect monodispersed microcapsules, we have to define the process parameters that lead to this intermittent dripping region flow you see here. So we fix each phase flow rates at a time to form operability windows like this, where we can see the flow rates required to achieve the dripping region and form our microcapsules, which only happens here inside the red curve. And also the combinations that do not form any capsule or form capsules with multiple cores that we are not interested in right now. Then, we described the diameter and the shell thickness of the microcapsules as functions of the process conditions by analyzing each point here inside the red curve. We established that we could control the diameter of the microcapsules by changing the flow rate of the continuous phase. The lower the flow rate was, the bigger the capsules would be. By doing so, we were able to produce microcapsules with diameters ranging from 130 micrometers to 260 micrometers. We also established that we could broaden this range by simply changing the device dimensions, so even smaller capsules could be produced. We also learned that the shell thickness depended almost exclusively on the middle phase flow rate, and we then produced capsules with thin and thick shells. With this study, we produced more than 100 batches of monodispersed microcapsules of different sizes and shell thicknesses. Some of them were selected to the following constriction experiments. This is the setup used. A fluid system was applied to feed the suspension through the capillary at constant flow rates and measure the pressure response. It enables the control of the flow rate as well as of the dispensed volume, as the applied pressure automatically adjusts in the background to maintain the flow rates. An inverted microscope equipped with a high-speed camera and a computer was used to monitor and record real-time images of the microcapsule's flow. The capillary used has a diameter of 300 micrometers and the constriction has 100 micrometers of diameter. Here is a list of the batches of microcapsules used in this experiment with their diameter and shell thickness. All of them are smaller than the glass capillary diameter, 300 micrometers, but bigger than the constriction diameter. To enable pressure drop measurements, microcapsules were suspended in a saturated sucrose solution to increase the carrier fluid viscosity, and results were all obtained at a flow rate of 0.2 milliliters per hour. Microcapsules can undergo two types of deformation during the experiment. It can either be a reversible deformation, in which the microcapsule returns to its original shape after flowing through the constriction, or the microcapsule ruptures at a certain level of pressure drop during its passage. Let's wait to see it here, the shell rupturing. Here we go. Looking more carefully to the capsule behavior during the flow, we see that during reversible deformation, the microcapsule arrives to the convergence zone as a sphere. This moment is related to the first pressure plateau that indicates the pressure needed to push only the continuous phase through the constriction. Then it starts deforming to fit to the constriction, presenting a slug shape. This partially blocks the flow, causing an increase in the pressure response. The slug shape remains inside the constriction until the microcapsule reaches its maximum longitudinal elongation. Then the microcapsule is expelled from the confining geometry and its rear becomes slightly concave. But its membrane integrity is preserved, which can be verified by the absence of leakage. The pressure starts dropping. After that, the microcapsule recovers its original spherical shape and the pressure reaches back the initial plateau. When the constriction causes the shell rupture, what happens is that the microcapsule takes the slug shape as it enters in the convergence zone. Because the pressure increase is not enough to make the microcapsule pass to the divergence zone, it gets stuck in the constriction until the shell ends up rupturing. Then the inner content is released to the medium and the pressure reaches back the initial plateau. Even though we were able to measure the pressure response in this case, the reduction mobility would be higher if rupture did not occur. Here is the list of the capsules used in the experiments again, now including the pressure drop and the type of deformation observed. At least 5 measurements were made for each batch of capsules. Here we show the average. Only capsules of batches 3 and 5 flowed intact through the constriction. For the last 2 batches, here 4 and 5, the ones with the smallest capsules, it was not possible to measure the pressure drop because it's below the instrument's resolution. Analyzing these results, we see that pressure rises with the diameter when shell thickness is fixed. This makes sense since it is more difficult for the biggest capsules to flow through the constriction than it is for the smallest ones. We can see it by comparing batches 1 and 3 and batches 2 and 4. A similar behavior happens when the diameter is kept fixed at the shell thickness. As the shell thickness is increased, pressure drop also increases. The batches 2 and 3, for example. So, diameter and shell thickness do affect the pressure response, but alone may not establish what time of deformation the microcapsule suffers. Nonetheless, it seems that these parameters can be properly combined to have a strong effect on how a microcapsule responds to external stress. Here we have a map that summarizes all data based on the ratio between shell thickness and microcapsule diameter. For a specific constriction diameter, the map shows that the correlation between capsule diameter and shell thickness defines if shell ruptures or not. It indicates that for a certain microcapsule to constriction diameter ratio, here, there is a minimum ratio between shell thickness and capsule diameter that guarantees reversible deformation and therefore microcapsule integrity after passing through the constriction. Thus, there are 2 zones determined by the mechanical properties of the microcapsules, a rupture zone and a reversible deformation zone. The capsules in blue with low shell thickness to capsule diameter ratio rupture, being suitable for target delivery triggered by the external stress imposed by the constriction, while the capsules in red with high shell thickness to capsule diameter ratio can be used for flow mobility control. Summing up, we were able to produce microcapsules with tunable mechanical properties and flow them through a constriction measuring the pressure drop associated to each phase of this flow. We established the conditions that lead to shell rupture associated with the shell thickness to diameter ratio. Our results show how microcapsules can be designed and produced to achieve the desired suspension flow behavior in confined spaces. I would like to thank all the funding agents, my research group at PUC, and you for the interest in this research.